Okay, welcome to the third module of item analysis. So just talking about finishing up on various ways to analyze individual items. So some other item discrimination indices. And indices just means markers or ways we can tell if something is discriminating. And again, when an item discriminates, it means that this one item, not the whole scale, but the item, is actually usable to discriminate on an outcome, usually something we're trying to predict. So GPA, whether you're getting A's or B's, pass or fail, performing your job or not performing your job, or in a clinical setting, possibly even diagnosable or not diagnosable to some psychological disorder. So we mentioned already in the previous slides that P is simply item difficulty. Again, that's just percentage who gets it right. And that's a good marker to determine just how common it is for someone to get an item right. And again, depending on what the purpose of the test is, if we're wanting to basically test basic proficiencies, we might want a whole series of very, very easy items. Just basically, do you know this very core information or not? If we're wanting to discriminate between our top performers, medium performers, and bottom performers, we probably want a mix of easy items, moderate items, and harder items. If we're simply trying to find the very best people or the people with the highest level of skill, then we probably want all the items to be difficult. So again, this is just a way we can ask, how difficult is this item? It's not necessarily giving us information, though, about validity. It's not telling us if it predicts or not. It's simply just how often do people get it right or not. So to discriminate, we need to, again, look at different groups. And we talked about a couple of equations looking at the splitting a sample by top performers versus bottom performers, and a couple of equations we can use. But we can also just turn back to the same tool we've been using for reliability and validity and use just correlations. So we can use a point biserial correlation, which is just a fancy name for one of the variables is continuous and one of them is dichotomous, two levels. So again, instead of running one of those hand equations we talked about before, we can simply designate people being in the top group or the bottom group as a variable, for example, in SPSS. So 1's for people that are top performers, 2 for people that are lower performers, and then simply run a correlation between that value and our predictor, our item. So assuming, and again, that the item itself is on a continuous scale. So again, this is only going to work if the measure or the item we're looking at is a continuous interval variable. So it wouldn't work on a multiple choice question or a true-false question, but it does allow us to look at, for example, a question that basically is on a 1 to 5 scale. Do people that say 5, are they more likely to be top performers than people that say 1's? So this allows us to discriminate between two groups, and the groups don't necessarily need to be equal halves again, so this is one of the advantages of this system. It's a little less accurate than the D we are calculating, however. So generally speaking, a lot of times we're going to turn to those equations we talked to before. We can also look at to discriminate with continuous data. So if our outcome isn't top or bottom performers, our outcome is on a continuous scale. So our performance rating, for instance, on a 1 to 5, or GPA on a 0 to 4-point scale, we can also just correlate, again, an R, correlation, our individual items' continuous score with that outcome score. This is also useful when cut points are many or unclear. So, for example, if we're really wanting to look at not just top and bottom performers, but are you likely to score an A, B, C, or D? Or if we're just really looking for general prediction, we're not necessarily looking for a cut point. We can use Pearson correlation if the data is completely continuous. There is actually a correlational technique that we can use with not ratio data, but ordinal data. So if we have ordinal data, normally we couldn't run a correlation, but there is an adjustment correlation we can call, which is called Spearman's correlation, that we could also use to look for this item analysis. So if we have an item that is categorical, but each category represents more of something, we could use a Spearman correlation. So the main thing to know about Spearman correlation is it's a form of correlation that we can run it assuming that at least one or both of the variables we're interested in are not interval or continuous, they're ordinal. And again, we can also use item discrimination indices, also measure internal consistency. High D's or R's suggest good consistency. What this means is basically we can actually, once we calculate either an R for each individual item or a D for each individual item, we can also then average those across those items to get a general index of the measure, not just the item. And the higher this total average is, that also indicates a high internal consistency. Another way we can look at items is, again, thinking about how they discriminate individually in prediction. And instead of just looking at the R's of the correlations, we also want to look at the scatter plots. So I've got a couple graphic representations of item difficulty and discrimination. So basically, on one axis, the vertical axis, we have the probability of a correct response. In other words, how likely is it that someone's getting it right or not, based on their actual ability that we measure later. For example, school performance or performance in the workplace. So our first example, item A, test takers of low ability tend to do better. So this basically means this is an item that actually highly predicts low performance if you get it right, or if you get a high score on it. So, for example, that might be like a negatively worded item. I like to steal from work. Those people that highly endorse that item were also our worst performers. However, people that actually said, no, I don't, and scored very low, were our higher performers. Item B would not necessarily show up as a high R correlation, but it might still be a useful item if this is what we want to measure. It basically is showing that test takers with a moderate ability tend to do better. So these are scores that basically, sometimes a way to think of this is I sometimes see these items where they're relatively hard, so people that really don't know the material get them wrong. But they're also, they seem tricky, and my top performing students basically worry and worry and worry over what's the right interpretation, and they basically psych themselves out and often get it wrong. While people that just kind of know the material, read the question once, see the answer, and go for it. So that would be an example of an item that would look somewhat like this item B. A moderate score people are taking well on the test. Now, a reason to run these graphic representations of how each item is going, again, different items might be useful for different purposes. It depends on what we want to use the test for. Generally, what we're looking for in graphic item analysis is something like item C. Test takers of high ability tend to do better. It's a good item, it's a correlation, and it's what we're normally looking for. So the higher the ability and the higher the likelihood of you getting the item right, strong relationship. Our final item is a graphical representation of an item that shows a high level of discrimination. So this would be a good one if we actually need a cut score to be used. It basically says that those of low ability absolutely can't get this item right, but at a certain level of ability, everyone can. This might be something like a basic level of musical ability. So if we're wanting to basically determine, can you play scales? Well, you either know how to play scales on an instrument or you don't. So if you don't know, you don't do it. You fail, 100%. If you know how there's a very few people that would mess it up once you know how to do it. It's a fairly easy thing once you've learned, which means we'd see an item discrimination like this. And again, if the test item is meant to simply tell us, does a person have a basic skill that you either know or you don't know, then we'd want to see a graphic representation like this. So again, this slide and the last is really just focusing on the idea that it's not always just about the percentage that gets it correct. It's not always about calculating a D or the reliability and validity. We also want to ask, what does it actually look like, how this item is predicting? And again, going back to that first of the 5 stages of test development, why are we making this test? In certain situations, each one of these examples might be something we would want, and in certain situations, we might not want an item that looks like this. So the final thing I'm going to talk about is utility. And the idea behind utility is a step past everything we've talked about so far. So when we're creating a test, we want to make sure, especially if it's multidimensional, that we have high reliability. And the higher the reliability, the more we can trust our validity tests. Once we have an acceptable reliability, we want to test to make sure that our measure is valid. It's measuring what we think we're measuring. And finally, what we've talked about today is, in the last 2 modules in this lecture, is how do we actually design the test and how by individual items, but also how do we actually check to see how each item is functioning. Do we want to pull out items? Do we need to put in more items? And if we put in more items, how are they working? The final question, once we have the test to where we're confident that the items are doing what we want them to do, we're confident that the items themselves discriminate on whatever we're trying to predict, that we have solid validity and evidence of validity, that we're measuring what we think we're measuring, and that it's a reliable test. The final question we want to ask as a test maker is utility. can this test be used? Is it a usable test that is going to be wanted by people that give tests? So utility is the usefulness or practical value of a test to improve efficiency in an organization. So one of the very first definitions I gave of psychological test and measurement was that it's a field that's focused on the assumption that these tests add value. That if you use these tests, you can better predict who will do well in school so that you're not bringing in people that will just fail. That if you use these tests, you can find people that will be better at their jobs and will also be more satisfied with their jobs. If you use these tests, you can better differentiate between people that might need extra training or psychological interventions. So the factors that affect utility include psychometric soundness. So generally, the higher the criterion validity of a test, the greater the utility. So remember, criterion validity is, does our test actually predict what we expect it to predict? In other words, we created a test for a purpose, whether it was to select people for a job, to select people to get extra training, to select people to get promoted, to select people that might need psychological counseling. Is the test strongly related to that outcome? If so, that's one of our first questions of utility. So all of the testing we've done up to this point is building up that psychometric soundness argument. There are exceptions because many factors affect utility of an instrument, and utility is assessed in many different ways. In other words, psychometric soundness is not the only measure of utility. In other words, a very valid, very psychometrically sound, criterion-related test may not actually be a useful test. And in the next couple of slides, I'm going to give some examples of why. So one factor affecting utility beyond psychometric soundness is cost. It's one of the most basic elements of utility analysis is how much does it cost to give out the test. So if you create a valid test, a psychometrically sound test, a test with high criterion validity, but it costs thousands of dollars. Let's in fact say it costs $500 to administer this test, $1,000 to actually score the test. So that's $1,500, and that's not counting the amount of hours it then takes for people in the organization to give out the test and also for people to take the test. So let's round it to an even $2,000. And what we're testing for is basically part-time labor, that the training of which costs maybe $100 to train someone to do the job. That's probably not a very high utility test. We spend a lot more money than it costs just to train a new person if someone fails. So the cost is in the context of the test utility refers to the disadvantages or losses or expenses, both economic and non-economic, when we look at a test. So when we're looking at utility, we want to ask what is the cost and what is the benefit. So if the cost of a test is $2,000, but the benefit is to save $100, that's a bad test. No matter how good the utility or how good the psychometric soundness, the reliability and validity is, it's not useful. No one's going to want to pay for that test. Now conversely, if that same test costs $2,000 and the cost of losing someone from an organization because they were a bad hire and the cost of training is $20,000, then spending $2,000 to find someone that is much more likely to complete the training and much more likely to stay with the company makes a lot more sense. So benefits, we should take into account whether the benefits of testing justify the cost of the administering, scoring, and interpretation. And benefits can be defined as profits, gains, or advantages. So what are we gaining out of the test compared to the cost? Now, this can be looked at just logically. You can basically try to estimate how much does it cost to give the test out and what you think the benefits are. But there's also some different ways to try to actually mathematically calculate utility. So utility analysis is a family of techniques that entails a cost-benefit analysis designed to actually estimate the specific amount of money you're saving or losing. So it's designed to yield information relevant to a decision about the usefulness or practical value of an assessment tool. And what we need to do a utility analysis is we need to have the decision accuracy. So we need to have that D. We need to have how often do we make a correct decision with this test. We need to know the validity. So how valid is the test? We need to know the base rate. Base rate is what was the decision accuracy prior to the new test. In other words, without the test, how often were you getting successful results? And finally, the selection ratio. How many people are applying compared to the number of people you're selecting? So if you have any 3 of these, you can calculate the remaining one. So generally what we're going to have is we're going to have validity, base rate, and selection ratio. And we're going to be calculating decision accuracy. So validity is simply the criterion validity of the test. How strongly related is this test to whatever the outcome is that you're interested in? Let's just stay on employment for now and say the likelihood of someone being a high performer. Base rate. Normally an organization is going to have the base rate. So how often does someone that we hire just randomly, we just select anyone that comes in off the street, how often do those actually end up being top performers? And finally, the selection ratio. Of the people that apply, how many of them do we actually hire? Now, that's a job example, but this could easily be an educational example. So how valid is the test of predicting performance? What was past performance base rate? So how many students were getting A's? So number 2, validity. How well does this test predict whether or not you'll get an A? Base rate. How many people were getting A's prior to using this test to predict for those that are going to get A's? And finally, how many students are applying to those that you get to choose? So there's a bunch of different ways to calculate this. There's Taylor-Russell tables, Nyland-Shine tables, the Brogden-Cronbach-Gleiser formula. I'm throwing a bunch of names at you. The end result, though, is there's a lot of different ways to calculate based on these 4 pieces of information. Validity, base rate, and selection ratio, the information you should hopefully already have, to then actually predict your new decision accuracy. In other words, what do you move the base rate to? We're going to look at an expectancy table, so I'm not expecting you to remember these. I'm just letting you know there's a lot of different ways to do it. We're going to look at an expectancy data table as a way to do this on the next slide. So here we have a Taylor-Russell expectancy data chart. And what we have here is the 3 pieces of information that we should already have, and then the calculation that we're going to do to figure out what our new actual decision accuracy would be. So we're going to start with a base rate. Our base rate in this case is 30%. Now notice on this table there's a base rate of 30%, and down below is a base rate of 70%. The actual total Taylor-Russell tables has a table for every single base rate in increments of 5. 5%, 10%, 15, all the way up to 100%. So I've chosen 30%. That means that currently, whatever selection technique we're using, let's say a quick interview and a gut feeling, means that of the people we're hiring, 30% of them actually end up being adequately decent performers. So that's a pretty bad base rate. And usually when we find a bad base rate, that's when there's a strong need for a better test. So we create a new test, we run it through reliability and validity analysis, and we find out that it has a validity coefficient of 0.3. So it predicts 30% of approximately 30%. So R is 0.3. The percentage is R squared. So 0.3 times 0.3, it explains about 9% of the total variance in performance in this case. Which again sounds small, but that's still 1/10 of the total of performance being predicted by this test. And when trying to predict human behavior, that's pretty good. The next thing we need to ask is selection ratio. So of every 100 people that apply for this job, how many does this company pretty much have to hire? And in this case, I've kind of randomly chosen 70. So basically, 7 out of 10 people that apply are going to get hired. Now, if we take our new test with a validity coefficient of 0.3, but we're using it on a situation where we're only getting to reject every 3 out of 10 applicants, so we're hiring 7, we just cross over into the table for the middle area, and that's going to give us our new decision accuracy. And it's 0.35. What this tells us is that if we use this test, the estimate of what the new decision accuracy base rate is going to be is now 35% success. So now it's up to the company to decide, is that increase in 5% in success worth the cost of the test? Now this table doesn't tell you that. You have to be able to put those numbers together. You have to ask, well, how many people apply? How many times do we have to spend for the test? And is a 5% increase in performance worth the money? But let's look at an example of a better test with a lower selection ratio. So this time we've got a very valid test, 0.70, highly predictive of success in the organization. So 0.7 times 0.7, this is explaining near 50% of the variance in performance. And we also have a much lower selection ratio. We've got 100 people applying, of which we'll hire 10. So now we have the ability to make a lot more fine choices. Our selection ratio means that we can effectively choose the top 10%. Remember, when our selection ratio is 0.7, we took 70%. Even if we're getting rid of the very bottom performers, we're still hiring a lot of people the test probably says we shouldn't hire. In this case, the selection ratio really lets that test shine. We have a highly predictive test, and we're only selecting the very top group out of that testing for our new performers. Again, we look across the chart, and now we find that that base rate is more than doubling. Where before the base rate of success in the company was 30% of the people hired actually ended up performing adequately. With this new test, we would estimate a doubling of that, 62%, which means the company is having to fire half as many people. And for every 10 people they hire, 6 of them end up working out instead of 3. Now again, unless this test is extremely expensive to administer, the savings of being able to retain twice the number of people you hire is probably going to make this a very high utility test. So again, just putting it all together, decision accuracy is about, again, our predictor on the horizontal axis by our criterion, the outcome, on our vertical axis. And again, we're looking at an approximate graphic representation of a correlation between our predictor, our test, and our outcome, the criterion. And the stronger that relationship is, the higher the validity correlation, the more likely we are to get hits. So again, those cross lines are cut off on our predictor battery. So if we look at the horizontal line predictor battery, we have 1/2 are being rejected and 1/2 are being hired. That creates our line that goes up vertically through our correlation. Meanwhile, within the organization, we have the criterion on the vertical axis. And in this case, we have those that succeed and those that fail. And again, the success line is basically minimum performance expectations on our outcome measure, the criterion, performance. And that creates that horizontal line that goes through our actual graphic representation of a correlation. That means that, again, this also is a way to graphically show utility. It shows that using this predictor battery, we're going to get most people into the Q1 quadrant. That's the hits. People that we say you should hire, and when you hire them, they actually do very well. Now, we're still going to have false alarms, that Q3 quadrant. Those are people that we said to hire that are actually failures. So this is a good representation, actually, of that last slide. In that, we have about a 70% validity coefficient, a very strong relationship, and it's moving it to where we're getting about 2/3 of our hires are successful and only about 1/3 of our hires are failures. Now, how utility is tied to validity is, again, if we start changing these numbers around. So we can also move our bar up. If we want to make sure that we only get people that are worth hiring, in that case, what we're looking at here is that increase. And what we're seeing is that if we actually set that cut line on our predictor battery higher, now we're only getting hits. But notice that about 90% of the people that are applying are no longer getting hired. So the only way we can do this is if we have a large selection ratio. There's a bunch of people applying, and we have the luxury of only hiring the very top. Now, in a low selection ratio, we're having to hire 80% plus. Notice that our predictor battery now is providing almost no utility. Because, yes, it's telling us the correct rejection, so the people it says not to hire truly shouldn't have been hired. But for the most part, we're having to hire a lot of people that are going to do well and a lot of people that are going to do poorly. We've still helped a little bit. We've gotten rid of some correct rejections. But because of our selection ratio, the company is having to hire just about everyone. No matter how valid that test is, it's just not having much utility in this situation. And that's the other thing, is the utility analysis reminds us that we have to get that selection ratio up to a pretty high number for any good test to really be worth running. So, looking at validity also, the relationship validity, so this is a pretty strong correlation. But if we actually look at a weaker correlation or a stronger correlation, we also see how this helps in our ability to predict, and therefore helps or hurts utility. So this is an example of near a an R of 0.9, almost around 85, 80% of variance explained. So this would be a pretty rare situation. But notice that our false alarms and our misses are very small in this situation. Even in the middle of a selection, we're only picking about half of the people. If we've got a test that has this much criterion-related validity, it is strongly related to our outcome, we can still get a lot of utility out of that test because the amount of people that we're misclassifying are very small. Conversely, this is often a little bit more like what we're seeing when we're actually using tests for prediction. This would be a good example of what the GRE looks like. It is useful. If we use the GRE, we are getting more hits than false alarms, but we've also getting a lot of false alarms, and we're also rejecting a lot of people that would have done just fine. So it's better than guessing. It's better than going with a gut hunch. But again, it shows that validity is strongly affecting utility. The less criterion-related validity we have, the less our predictor is related to our outcome. Also, the less utility or successful usefulness of the test. And if we have no relationship between our predictor battery and our criterion, then we have no utility whatsoever. You might as well just flip coins.